So for the next session, we have a lab tour planned for you. And to do this, we welcome our speaker, Isabella Goetting. And today we have her as a speaker, and we're very excited to welcome her. Isabella is a fifth-year PhD student in the physics department at Duke University. She studies quantum networking of trapped ion quantum computers in Christopher Monroe's lab. Along with her research, Isabella values science communication and increasing diversity and equity within the physics and the broader STEM communities. Outside of physics, she enjoys powerlifting and spending time with her friends and her dog, Dakota. Welcome, Isabella.
Thank you so much for the wonderful introduction. I'm Isabella. I'm actually in the lab right now. So I'm going to play for you guys a little video that we put together of the lab tour, and then there'll be plenty of time for questions. So if there's anything you want clarified or want more information on, we can definitely discuss that. So we work with trapped ions. So an ion is simply an atom where you remove an electron. So it's a charged atom. And each ion we use as our qubits. We can pick two specific energy levels within an ion as our two qubit states. And we can manipulate those states using lasers. Hi, welcome to the Duke Quantum Center. My name is Isabella Goetting, and I'm a PhD student in Christopher Monroe's lab at Duke University. We study quantum networks for trapped ion quantum computers.
And my name is George, and I'm a postdoc in the same lab. And so today we're going to show you around the lab, but before that, let's have some background.
Okay, so what are ions? Ions are simply atoms with a charge, and we use ions as our actual qubits. In order to control our ions, we use lasers. So each ion has discrete energies that correspond to specific wavelengths of light. Think of a ladder with uneven spacings between the rungs. It will take more energy to reach the next step if it's farther away, but less energy if it's closer. This is similar to what happens in atoms. An atom will absorb light that corresponds to a specific energy difference, and after some time, it'll spontaneously emit that light, which we can collect in the form of photons. This tells us what state the atom is in. Now, if we translate this to qubit technology, we can choose specific energy states to be either 0 or 1. So this is what a trapped ion quantum computing chip actually looks like. We call this a surface trap. It has electrodes in it that help control the ion's position and can move them around. These ion traps live inside vacuum chambers, and they can trap about 15 to 30 ions in a single chain. Now, in order to do useful computations with quantum computers, we will likely need millions of qubits. But there's a problem. If we keep adding more and more ions into our single chain of ions, it becomes more difficult to individually control them. Think of being in a room with people. It's really easy for me to hear George if it's just us two speaking in a room. But if more and more people start entering our lab, it becomes increasingly more difficult to hear George speaking next to me. That's kind of what's happening to the ions if we keep adding more in their chain. We call this spectral crowding, which means their frequency spectrums are getting more complicated as more of them interact with each other. So we need a way to control them while still having access to more ions.
And that's where we come in. We use single photons as interconnects between smaller ion trap modules in order to build up a quantum network. By interfering these emitted photons, we can herald our ions into entangled states, and in this way, open a line of communication between the modules. Let's go take a look at what this physically looks like.
Okay, so first we have a laser table that houses all of the different lasers we need in order to control the different ion energy levels. We collect all of that light into optical fiber and send it over to our chamber table, which is here, to actually control and manipulate the ions. Let's take a closer look at the laser table. So we trap two different kinds of ions, barium and ytterbium, and they both have very different spectrums of energies. So we need a lot of different lasers to control all of the different levels. So this table is just for the lasers, and we have even more in drawers over there.
this here is our qubit laser. So this laser is a green laser, and it produces green light which cycles the ion between the two qubit states. And then over here we have an optical cavity, and that is a really stable device that we lock all of our lasers to keep them so that the frequency doesn't move all over the place. And over here we have our 1762 optical qubit laser, which is locked to an even more stable cavity, and it's under vacuum, as you can see.
Okay, so this board over here has our photoionization lasers. So this blue-purple light is at 413 nanometers, and what this does is when it goes into the chamber and hits the neutral barium atoms, it strips away an electron, turning it into an ion. And moving over here, this really big laser is called a Tisoff laser, and it outputs light at 986 nanometers, which we can't see. But this is what we use to generate our single photons from the barium ions. So the light travels through this thing, which is called a pulse picker. So it allows us to pick out only one pulse to send to the ion so that we only get one photon. Then the light travels through a crystal that's inside of this oven, which frequency doubles it to 493 nanometers. This is a really pretty teal color, and this is the color of our single photons. The light then travels over here and gets split into 3 paths to go to each chamber. Okay, so I've mentioned this 493 nanometer light, which is the color of our single photons. It's this really nice teal color, which you can see in this laser drawer here. Isn't it pretty? Okay, so I said that we collect all of the laser light into optical fiber. So this is what an optical fiber can look like. And we put all of the fibers into this blue loom here, which we then send upwards and over to the chamber table. So the fibers come out here, and we send them into some optical elements such as mirrors, and we can shoot it then into the chamber.
So how do we check if fibers are clean? We use our fiber inspection scope. Here you can see a picture of a really nice fiber, and if you work in the optics lab, we'll tell you that you should never touch your own fiber, because this is what happens. Ew, you wouldn't want that.
Okay, so we have 3 different chambers in our quantum network. This one right here is Bob, the middle one is Cleo, and the one in the back is Alice. So each chamber can trap both barium and ytterbium. So ytterbium is nice as what we call a memory qubit because it's largely insensitive to magnetic field fluctuations, meaning that it can hold on to information for a really long time. Barium we use as our communication qubit because it emits photons in the visible spectrum, so we can actually see it. And a lot of technologies are more efficient in the visible spectrum. Barium is sensitive to magnetic fields, so it's not as nice of a quantum memory, but it is great for our communication purposes. So this black tube right here houses our really big lens. It has a numerical aperture of 0.6, which means that it can collect 10% of a solid angle emitted from a point source. So this is what we use to collect our single photons from the ion. So we then collect that light into this optical fiber, which we can then use to interfere the photons from different chambers. Okay, so I mentioned how we collect single photons into fiber, as shown here. So this is a probabilistic process, meaning that we have to do it a bunch of times in order to actually collect the photon into fiber. So our overall collection efficiency is about 2%, which sounds quite low, but this is actually one of the highest efficiencies using these really big lenses. So first, we have to entangle our ions with the single photons that they emit. How do we do this? So I mentioned earlier that we hit the ion with a really short pulse of 493 light so that it gets excited and will spontaneously emit. And when it emits, it'll emit a single photon. So when it spontaneously decays, it can go to one of 2 states in its ground state. Depending which state it falls down to, it'll either have horizontal or vertical polarization. And polarization, what is that, you may ask? Well, think about when you're at a gas station, for example, and you have your sunglasses on and you're trying to read the number on the screen and you can't really see it. That's because your sunglasses are polarized so that it only lets light of a certain direction through your glasses. So once we collect that photon, we don't know if it's horizontal or vertically polarized, so it's in a superposition. We then collect a single photon from a different chamber as well, and the photons will travel through their fibers into a 50-50 beam splitter. And all that does is that when the photons go through this beam splitter and they come out, we no longer know which chamber the photon has come from. So then the photons will travel into something like this black box where we will interfere these two photons, and then we detect them with our single photon detectors. Here's a little cartoon of what it looks like inside of there. And depending on the click of which detectors will click, we collapse the superposition of the photon state, and it actually leaves the ions into an entangled state. So by doing this, we essentially open up a line of communication between ions in completely different traps. So this is our middle chamber, Clio, and it's pretty cool. So instead of having its really big lens outside of the chamber like I showed you over there, it has two in-vacuum lenses that are really big. So each lens has an NA of 0.8, meaning it collects 20% of the solid angle emitted from a point source. So having something like this is pretty cool when you want to do long distance networking. So optical fibers have attenuation, meaning it'll kill the photon the longer and longer it travels, so that by the end of your fiber, you'll have no more signal. So instead, we have something called quantum repeaters. In quantum mechanics, you cannot directly copy a state. So instead, we have this quantum repeater in which we basically transfer information onto a different ion and then entangle it with the next node in your system. And in that way, we can transmit information over longer distances.
Okay, so this here is a picture of an ion. So this ion was trapped in the Bob chamber, and what we do is we hit the ion with 493 nanometer light, and then the ion fluoresces 493 nanometer light, which we collect an image on a camera in order to show you this picture. And the image of the ion looks a little funny or astigmatic because the objective was not perfectly aligned to the ion. Ideally, it should look like a circle.
So in our lab, we have this list of names of people who have worked on this experiment throughout the years. And on the right, you can see our remote entanglement generation rate increasing over the years as well. The main difference in why the rate has increased so much in the recent years is the move from using ytterbium to barium as our communication ion because of that nice visible wavelength. Thank you so much for listening to this lab tour. Please let me know if you have any other questions.
All right, so let's see what's coming in on Discord. Looks like Crystal was there just 2 weeks ago. Not a question, but it's exciting to see that the space is recognized. We've got a question. Do you have a picture of the atom as a circle?
I was trying to find a nice one, but we have to do something called fiber coupling, which means that we have to move around our fibers so that it can collect all of the light possible. It's circle-ish. Can you see that? The
Yes.
black and white one. Yeah. So it's a little bit uglier. I kind of like when you see, so the picture I was showing in the video is like a heat map. So the more photons, the redder the color is.
Sujal from India, how is trapped ion quantum computing different from neutral atom quantum computing? That's a really good question.
Yeah, that's a great question. So they are similar in a lot of ways in that you are dealing with an atom. I mean, the main difference is that just that ions have that charge. So the way that we actually trap the ions are a little bit differently, and that the way that they interact is different. So they can interact through like their Coulomb charge, which allows us to do slightly different things. We can look at different Hamiltonians to evolve through that spin-spin like interaction. The way, so neutral atoms typically you can trap using like tweezers, optical tweezers. So essentially you're sending this laser in and it creates a potential well. Whereas for ions, we have these electrodes on like the surface trap that I showed you in the video that can control its position. So it has that charge, so we can use the electric field to actually move it around. The traps tend to be a bit deeper, so stronger confinement. So the ions can typically live longer as well. And so one of the issues with neutral atom quantum computers is when you detect your atoms, you can destroy them quite easily. So they'll leave your trap. Whereas ions, we don't typically have that issue because it's a stronger potential. What's nice about not having a charge is that you can have these really big neutral atom arrays. So if you think of like a lattice structure and there's an atom at each lattice point, you can have this really nice big array of them. And so scaling them can be easier in that sense. And that's kind of what our lab is focusing on is, how do we scale up these trapped ion computers, get more ions so we have more qubits. And we're using this approach of photonic interconnects, which, by the way, the photonic interconnects technology is largely platform independent. Like this could also be used for neutral atoms, and it's likely that most platforms will need some form of photonic interconnects in order to have like millions of qubits. Did I answer your question?
Thank you. Yeah. So we have another question, which is, there's no name on this user, but is there any specific reason that we use red light? That's quite a good question.
Yes, you're talking about like the red light in the lab tables. Yeah, there is actually. Yeah, it's kind of funny. People will come in for tours and be like, ooh, party lights. But yeah, so because our single photons are blue in color, we have our single photon detectors that are very, very sensitive to that wavelength. So when we have to work on the tables and close the curtains, we're in the dark, but we still need to be able to see. So we put on these red lights, which is the most different wavelength from blue that's still visible. So we can actually see and work in the dark.
Oh, very cool. Thank you. Another question. So how does your platform address scalability challenges, such as ion heating?
So there's kind of two main methods right now for, at least for trapped ions, on how to scale them. One of them is just having them all on a chip and then having different zones. So you can have multiple chains on a single chip. And then they do something called ion shuttling. So you use the electrodes and you can move the ion's position around the chip. So you can imagine you have an ion in one chain, you do some circuits, and then you move that ion to another chain, entangle it with that chain, and continue your circuit. Atom shuttling is very expensive in the sense that it is slow and it heats the ion. So when you move the ion, that actually heats it up quite a bit. For photonic interconnects, which I showed you, we don't have to worry about that as much because we're not actually moving the ion around, it's stationary. You do have to worry about heating when so the excitation light that we use to generate that single photon. So if you keep hitting the ion over and over again with this strong excitation light, you can heat it up as well. So we do need to stop every so often to cool it back down. And this does affect the entanglement generation rate, not so much the fidelity, more of a rate hit. So it shows up in kind of a different way.
Cool. Thank you. We've got a question from Sergio in Spain. So he wants to know, when you say the ion emits and the photon is in superposition, how do you ensure the superposition is not broken by coupling to the optical fiber nodes?
Yeah, it's a great question. So when we couple the light into the optical fiber, it actually helps us. So it projects the light into this horizontal versus vertical basis, if you will. So when the ion is emitting light, this light has a certain emission pattern. We like to call it the peanut and the donut. And when we collect light perpendicular to the magnetic field axis, which let's just say it's, up, down. And so then you have this peanut shape and then a donut shape. And the peanut versus donut corresponds to two different polarizations. And when you couple the light into the fiber from that direction, it actually very nicely cancels out so that you have an equal amount of horizontal and vertical. And once you go into the fiber, it's a single mode fiber. So it's going to maintain that mode once it's coupled, and it won't mix it once it's in the fiber. So it actually kind of helps us. But you do allude to a certain issue, which is called polarization mixing. So when the photon comes out of the vacuum window, there's some what we call nonlinear birefringence on the window. So that just means, well, when we put the window in the vacuum chamber, we have to clamp it down. So there's going to be some strain on that window. And so when the photon passes through it, it changes the polarization of the photon in a nonlinear way that can be very difficult to correct for. So that can result in polarization mixing, where we think we have a horizontal photon, but it actually has a little bit of vertical in it. And this can hurt the fidelity of your state at the end. This is a hard problem that no one's really found a good way of solving. But what we did is we switched from using polarization to timing as our qubit basis, which I can talk more if you're interested. But yeah, so that's how we got around that polarization mixing problem, because then we just have one polarization and that's easy to correct for.
Thank you. We have a question from India. So is there any quantum cooling agents you use to address heating due to scalability?
So when we got that really high rate of remote entanglement generation of 250 per second, which is the current record right now, but in order for it to actually be usable, it should be on kilohertz rates. So we're making progress. But in order to get that high rate, we added in another ion, a ytterbium ion, which is a different species, and it works in the UV regime. So when we send visible light into the chamber, if it hits the ytterbium ion, it doesn't do anything because it's not resonant with any of its energy levels. But it has a similar-ish mass to barium. So through their Coulomb force and through their interacting forces, it can what we call sympathetically cool the barium. So by having the sympathetic coolant, we don't have to stop as often to cool down the barium ions. So we can continuously hit it with that excitation pulse and continuously attempt entanglement generation without needing to stop and cool. So Quantinium, I think, does this. They have ytterbium and barium, and they use ytterbium as their sympathetic coolant. We just do Doppler cooling. There are other ways you can do cooling. There's something called EIT cooling, sideband cooling, so we can actually get to a lower limit than what Doppler cooling allows you to do.
Thank you. Let's see. Sapphire is asking, do you use continuous wave lasers or pulsed lasers for ion excitation?
So for the excitation, we actually use pulse lasers. And you can use CW, however, that typically means that you probably wouldn't want to do it at 493. So the reason why we use pulse excitation is because we only want to get a single photon. So our pulses are about 3 picoseconds long, and the lifetime of our excited state is 8 nanoseconds. So 3 picoseconds is a lot shorter than 8 nanoseconds, which basically ensures only a single photon will be emitted. Whereas if you use CW, then you're going to need to use something called an AOM, which stands for acousto-optical modulator. It's just a fancy word that basically allows you to, it changes the frequency of your light, and we can use it as a switch. But these things are not fast enough in order to send less than a nanosecond pulse. So typically just the rise time for one of these devices is 10 nanoseconds. So they're quite slow, which is why we switched to a pulse laser for that.
Thank you. So I know we're coming to time. So one other question is, what do you enjoy the most about the work you're doing right now and working at the Duke Center?
I guess so. We actually had to move the lab down from University of Maryland down to Duke in my first year. So having to rebuild the lab was a lot of work, but I learned a lot about the system. And so now that we're actually running experiments and getting to kind of see the fruits of our labor, I'd say that is probably something I enjoy the most, is now getting to do the science part and seeing how everything works together. I think that, and also doing something like this where I get to communicate what we do and help people understand is what brings me a lot of joy.
Yeah, thank you so much for being with us today. It's been
Yeah, of
it's a
course.
really great lab tour. I really enjoyed it. I'm
Good.
sure everyone else did, given the questions. I know that you're on Discord as well. If you do have the time, I'm sure everyone will be asking you a million questions. So to everyone watching,
Yeah,
please go
sure.
easy on Isabella, because already given her time generously.
Yeah, no, for sure. I can definitely help answer some more questions on Discord. Also, feel free to email me or contact me at LinkedIn.
Thank you. Abhinaya, I'm going to hand over to you for closing and kind of any highlights that I know are coming up in your exciting program.
Thank you. Yeah, thank you, Isabella. That was amazing. I have actually never seen the workings of a quantum lab, and it was actually really fun to see.
Oh, cool. I'm glad you liked
Yeah.
it.
Yeah, thank you so much for taking the time to show it to our participants, and we really appreciate it. That's all we have for you. Thank you so much. Have a great rest of your day. Bye.